Hello everyone, welcome back. Starting from this lecture, we'll be spending 2 weeks to talk about greedy algorithms. Greedy paradigm is a really simple and interesting idea, and it can be used to solve a very large collection of problems. Okay, let's get to it.
Again, we will learn greedy paradigm using case studies. We will show 5 problem instances and their greedy solutions. Suppose we are planning a trip from Kingston to New York City. Wish those travel days come back soon. Suppose that there is only one fixed road, so we don't have a choice of which route to take. Our car will need several stops to fill up the gas tank. We know the location of all the service stations on the highway between Kingston and New York City, and we know exactly how far we can travel on a tank of gas. The goal is to minimize the number of stops we make along the way. The intuitive solution we have, perhaps, is to go as far as possible on each tank. That is, we only stop at a service station if and only if we cannot make it to the next one. Does this give us the optimal solution? It turns out that in this case, our intuition can be trusted. This is the right solution. Now the questions are, how can we write an algorithm to formalize this idea? Is this an efficient algorithm? Does it always find an optimal solution? Can we prove it? Next, we'll get to these questions one by one. First, we make clear on a few assumptions of the problem. We assume that this problem has a solution. That is, when we fill up at a gas station, we know we can always reach the next station. Otherwise, we can immediately say that there is no solution to this problem. Second, we assume that we know the distance between any consecutive stations, and we always know how much gas left and how far it can cover. Again, the idea is that once we have filled up the gas at a station, let's say the station is SI, we try to go as far as we can, so we only stop at the next station SI plus 1 if we cannot make it to the station SI plus 2. If that's the case, we stop at SI plus 1. Otherwise, we keep going and we check whether or not we have to stop. So that'll depend on whether or not we can make it to the next station SI plus 3. We see that we can restart this process whenever we stop and fill up the gas. So this idea can be easily realized using a recursive algorithm. So here is a recursive algorithm. We first sort all the stations based on how far they are from Kingston. SN will be New York City. For the recursive algorithm, RoadTrip, we are leaving station SI with a full tank of gas. ST is the next station. When T is less than N, we're not yet at the destination, and if we can reach ST plus 1 without stopping at ST, then we do not stop at ST and keep going. This while loop breaks when T is N or when ST plus 1 is not reachable. If T equals N, we know we have arrived, else we have to stop at the station ST and fill up the gas. Then we can restart and call RoadTrip ST. We find the solution of the original problem by calling RoadTrip S0. What's the complexity of this algorithm? Sorting the stations takes big O of n log n time. Choosing the stations where we stop takes big O of n time, since we look at each station exactly once and decide in constant time whether or not to stop there. So the entire algorithm takes big O of n log n time. Now, can we prove this algorithm finds an optimal solution? Now we look at the proof of correctness. This is, in fact, the more challenging and interesting part. We will use proof by induction. Proof by induction is a mathematical proof technique. To prove that a statement Pn holds, we first show the basis that P1 holds, and if Pk holds, we need to show that Pk plus 1 also holds. So for the basis of this problem, if n is 1, there are no possible stops between Kingston and New York City. We then see if we can make it to New York City on a single tank. We either have a single optimal solution or the problem does not have a solution using this algorithm. Now the inductive hypothesis. We assume the algorithm RoadTrip finds an optimal solution when we have a full tank and there are k stations ahead of us. In order to prove by induction, we need to show that the algorithm RoadTrip can find an optimal solution when we have a full tank of gas and when there are k plus 1 stations ahead of us. Again, let's make clear what we are doing here. Given that when there are k stations ahead of us, our greedy algorithm can find an optimal solution. Now we need to prove when there are k plus 1 stations ahead of us, the greedy algorithm solution is also optimal. Let's write the solution given by our greedy algorithm as a list of t stations that we need to stop. Now we need to take 3 steps here to show that this solution A is an optimal solution. First, we need to show that there exists at least one optimal solution that starts with our greedy algorithm's first choice A1. Second, the rest of our greedy algorithm solution from A2, A3 to AT is optimal for the reduced problem after we stop at A1. 3. When we combine the algorithm's first choice, A1, with its solution to the reduced problem, so that'll be the rest of them, we get an optimal solution to the original problem. First step, let's show that there is an optimal solution that begins with our greedy algorithm solution A's first choice, A1. We assume there is an optimal solution O that chooses stations O1, O2, and OR. So we don't know what those stations are, but we just need to know how they compare to the solution A. Now here is a question. Which station comes first, A1 or O1? It has to be O1. Recall how A1 is decided by our greedy algorithm? It is not possible to reach any station beyond A1 on the first tank of gas. So O1 could be the same as A1 or a station closer than A1. Now another question. If we stop at A1 and fill up the gas tank, can we get to O2? Yes, because the distance between A1 and O2 is no longer than the distance between O1 and O2. Since we can fill up at O1 and get to O2, because this is a valid solution, O, we can also stop and fill up at A1 and get to O2. Now we write another solution, O star, where we replace O1 of solution O with A1. We know this is a valid solution because we can stop at A1 and get to O2 and so on. We also know O star is optimal since its cardinality is the same as that of solution O. Looking at the 3 steps, now we have done the first one. Now the second step, we know this is true. When we fill up at A1, there are one less stations ahead of us. That is, there are only K stations. Based on the inductive hypothesis, when there are K stations ahead of us, our greedy algorithm can find an optimal solution. Now we look at the third step. Can we combine A1 and A2, A3 and show it is an optimal solution to the original problem? We know both A2, A3, AT, and also O2, O3, OR are solutions to the reduced problem after we stop at A1. We also know that the cardinality of A2, A3, AT is no greater than O2, O3, OR. Since we know A2, A3, AT is an optimal solution when there are K stations ahead. Since adding A1 to both these sets give A and O star, it is clear that the cardinality of A is no greater than that of O star. Since O star is an optimal solution, we know the cardinality of A must be equal to that of O star. Thus, A is also an optimal solution. This completes the proof that our greedy algorithm finds an optimal solution to the road trip problem. The fundamental principle of greedy algorithm is to take the best thing first at the moment. Greedy algorithms are often used to solve optimization problems following these steps. First, we sort the objects according to some criterion. Second, we repeatedly select the next item under constraints until no more selection can be made. As you can probably tell, such a simple idea may not work all the time. We'll see more on that later. Please really take your time and make sure you understand the algorithm we discussed today and its proof of correctness. A quick exercise is to convert the recursive algorithm to an iterative algorithm. I will see you in the next lecture.